Okay then, let's start today's lecture. Uh, I'll let the guys in when they will join. So, can somebody just confirm whether I'm audible or not? Agam, am I audible? Yeah, thank you. So today is the fourth week problem solving session of the control system lecture series. So in this lecture, I have taken few of the questions, but in those questions, most of the concepts will be cleared. So the first question is there is a second order system. This is the given by this equation. We need to find the natural frequency, damping ratio, rise time, peak overshoot, and settling. Before proceeding, I would like to highlight some of the concepts or some visualization that will help you solving any kind of second order question. So first, can somebody type in the chat if it's a second order system, how many poles the system will have? I'll write the question. Sorry. How many poles a second order system may have? Agam or Saurabh, anyone in the chat? Okay, so I'll answer this. Agam says two. It's correct. So a second order system generally has two poles in the S plane. Okay. So if it's a third order or fourth order, accordingly, number of poles will depend. So when it's a second order system, then the pole location. So just imagine this is my S plane. This is real, and this is imaginary. Okay, I will take some cases. Okay, then we'll analyze the situations. Forget about the question right now. I will be coming back to the question again. So just focus on like what I want to say. The pole locations can be, if it's a second order system, two poles, then the pole locations can be, I'll take some other color, maybe red, this, or like this, or let me erase these things, or the both of the poles are at the same location, or like this, or on the right hand side plane similarly like this, and the similar expression. I will draw another one like this. Okay. uh, let's take this as A, this is B, this is C, this is D, this is E, and this is F. Is there any other situation where the second order system poles can have? In general, no. Like on the right hand side they can have, but another thing, is, is this system possible? Like the system pole location, one is like this and other is like this. This is a second order system. This is explained. Type in the chat yes or no. Uh, with if you will be correct or you might be knowing something new concept. So this pole location, it's a second order system in the S plane. Is the pole location like such kind of pole locations are possible or not? Raghav says omega n3 and damping ratio. Raghav, I will be coming back to the question. Before that, sorry, Raghav, beg my pardon. Raghib, I will be coming back to the question. Before that, I am discussing some concepts, okay, which is not available in the lecture series or some books, okay. So, Agam says it's no. Anyone else? Uh, if this pole location configuration is possible or not? I want some other answer. It doesn't matter. You will be correct or wrong, okay. So, try to participate. Balkiran or Shiva Kumar, Aditi. My question is this pole location configuration correct? Okay, I won't take much time. So this is not correct. Absolutely wrong, because whenever poles exist in imaginary axis or any real, they exist in imaginary pole pair. So whenever it's not real, it has some imaginary value. This is the real axis and this is the imaginary axis. Then they will, if it exists in the imaginary, it has some imaginary component, then they will exist in pole pair. So there must be some pole like this. So it's a third order system, not a second order system. Similarly, if it's a fourth order system, this kind of and this kind of situation is possible. But I will just uh, make like this. This is not possible. Whenever imaginary numbers, complex numbers exist, they exist in pair. Okay, because when you solve the characteristic equation, it's s some real plus or minus j root over something. Okay, keep in mind, complex poles doesn't exist in isolation, they exist in pair. Having said that, come back to the this situation, the a b c d e f. So these are the all possible configurations. So let's take some real examples. Like I will take, okay, 1 second. Okay, so let's take some real values. Like let's assume this is the S1. The poles are at uh, plus or minus 5j. Okay, this is at some minus 0.5 plus or minus 5j. This is at minus 0.5 and minus 0.5. This is at some minus 1 comma minus 0.5. This is at some positive value, so plus zero point 0.5 plus or minus 5j, and this is some plus 0.5 and 1. Is it correct? Okay. Are you following, guys? Can I get some yes or no? Okay. Okay, cool. So what I will do is I will try to plot them. Then you will get the response, like how they behave, and you can get the visualization. Why it's important, this concept. So I'll stop sharing and I'll connect from my laptop. One second. Okay, there is some issue. Okay, can you see my screen, my tab? Okay. This tool, the Ulfam tool, is very useful to analyze by your own. If you are not exposed to MATLAB, then this can solve. So you can see there is a it calculates the inverse Laplace for you can see my mouse pad, right? The cursor. Okay. So we know it's the Laplace transformation of s square plus 1. So it's the inverse Laplace transformation of sine t. Simple. So that's why the plot you can see this. It's the sine t. Can somebody guess the pole locations of this case? The pole location for this 1 by s square plus 1, it's plus or minus j. Yes, very good. So according to our example, let's take this is 25, so or some 5 or something, and okay, let's take it 5 only, 1 only, and let's take this 25. Okay, so the pole location should be plus or minus 5. Now see, it's pure oscillation. Okay, there is no damping, nothing. Now comes, because the pole locations are on the imaginary axis only, there is no real component. So as the second condition, my poles were minus 5 plus or minus 5j. So what I will do, just add plus 0. Okay, so look, this is the uh, condition. Now s plus, so this will have, you can verify this will have the poles at minus 0.5 plus or minus 5j. Look, now you can see the oscillations are being died out. As the time increases, the oscillation is dying out. As time, if we take time is equal to infinite, it will be converging to 0. Now let's take the third example, the third condition which I had taken. Both the poles at minus 5, minus 5. Okay, let's see what happens. Now you see the the plot is like it's getting some overshoot, then it's coming back to 0 value. It's just both the poles are at minus 0.5. So you know, for only a single pole at minus zero point 0.5, this is s plus 0.5. So the pole is at minus 0.5. The response was like that. From some initial value, my infinite, it will come back to 0. So when the both the poles are at that value, just a second, I'll let somebody in. Okay. So now come to the next condition, which was one pole was at 0.5 and the second pole was at minus 1. Now you can see, okay, it's the similar plot. Okay, there is no frequency, like no oscillations at all. I'll come back to the slides again. Now let's go to the right hand side plane. Okay, we started with s square plus 25. Okay, the simple sinusoidal. Now let's go to the right hand side plane. So s minus 0.5. Okay, now look, now my oscillations are increasing in its magnitude. So my system became unstable. So I will come back to my slides and stop sharing. 1 second. Okay. So This had a behavior of pure oscillations. This had a behavior of oscillations dying out gradually. This had the oscillations like it that didn't have any oscillation, it just went up and died out. This had the similar but at a faster rate, at a slower rate. Okay, this will you will get, and this exploded like uh, like this, and this also, this can you can verify, this will also go beyond. Am I clear? If is this concept clear? Because here both the poles are in the left hand side, that's why the system is stable. And this we, if we divide it into two components, this will be calling as omega d, and this will be calling as theta omega n. So whatever the pure frequency the system had initially, the initially point the 5 hertz, the plus or minus 5J, that is called the system natural frequency. Initially, when the system didn't have any damping, what is the system's frequency? That is called the natural frequency. Now, when the damping is introduced, then the omega d, this omega d is called the damped frequency. There are two terms, so you can get. So that's why, because of the poles in the left hand side, it died out and it will converge to zero. Okay. If this okay, okay. I'll repeat. So when the system look at the case test case A, test case A, both the poles are in the on the imaginary axis. Okay, it doesn't have any real part. That means it's a pure sinusoidal frequency, pure frequency. Okay, you can see the plot. It doesn't converge to zero, neither it goes like diverges like the test case E. That's why this is called the natural frequency of the system. When there was no hindrance, there is no damping, the system has this natural frequency. But in real life, uh, you can take the example of a simple pendulum. When you oscillate the pendulum, after some time, it converges to zero because of its damping. If damping is not there, you oscillate the pendulum in space, it will constantly keep on oscillating forever because there is no damping in the form of air drag. I'm not gonna teach air drag or something. There is the damping coefficient. That's why the original system had the natural frequency omega n, which is called omega n, that is called the natural frequency. When the damping is introduced, then the frequency a little bit decreased, that is called the damped frequency, omega d. Am I clear now? No. Significance of uh, the real part, like it will introduce, uh, like if it's a simple pole, it's A, it's at minus A, then you can say e to the power minus at is its response. Correct? So this e to the power minus at, its response is like it will come from infinite to zero. And you are like this, the system, the this plot, like when the poles are at on the third and fourth, this complex conjugate, then the system, this vector has a real part and some imaginary part. I can write it as a plus jb, then this is b and this is a. The b part will try to make the oscillations, but the a part will try to converge it. But when they are both are combined, when you are on xy axis, you try to go to on x-axis, and you try to go on y-axis, one unit, then ultimately you will convert like this. Similarly, the B part, the B will try to keep on oscillating, and A will try to make it converged. But that's why when the both are combined, the system oscillation will be like this. This the got it now? Okay. Okay. Good. Thank you. Then now I wanted to make you visualize the plots. Like now, whenever there is a situation, you have both the poles. You can plot or you can imagine the plots. Then coming back to the original question. Okay, I'll erase this part. The question is, my second order system is given like this, and I need to find the natural frequency of the system. Okay, so using Laplace transform, I can get and zero initial condition. This is very important. I am repeating again and again. Initial condition. I'll get s square y of s plus 3 s y of s plus 9 y of s is equal to u of s. Then my system g of s will have y of s divided by u of s, y of s divided by u of s is equal to 1 by s square plus 3s plus 9. Okay, so can somebody just tell me, like, okay, sorry. The first question, what is the natural frequency of the system? The general second order system can be written as k into omega n square divided by s square plus 2 zeta omega n s plus omega n square. This is a standard second order system expression. Okay, and where the omega n is the natural frequency. So converting this to similar expression, I can write 1 by 9 into 9 divided by s square plus 3s plus 9. Okay, then what's the natural frequency? It's 3. Okay, the natural frequency is 3. And what is the damping? The damping zeta, we can equate 2 zeta omega n is equal to 3. That means zeta is equal to 3 by 2 into omega n. Omega n is 3. That's why zeta is equal to 0. Or half. So it's half. Am I clear up to this part of the question? Or somebody has some doubt? Okay, cool. Thank you. Then coming to the third question. What is the rise time? So as you must have seen, okay, here I will try to solve this C part. Uh, okay. Uh, you might have gone through the lectures, because if I will explain those concepts again, it will take a lot of time, and we won't be solving all the questions I have taken today. This is for unit response of second order system. Then, okay, this is kind of the typical second order system to unit response. So this from 0 to till it reaches one value, that is called the TR, rise time. Okay. So does anybody remember the whole formula of the second order system in a, like, given? I'm not asking the this formula only, rise time. I am asking about the whole y of t formula, because you remember this formula, then all the questions will be solved. And mind it, this kind of question you will get in your, if you are a student, you will definitely get in your examination, step response or a unit impulse response. These two questions are very much important. You need to be deriving it, or you need to. So one expression I want you guys to remember. Like I generally don't encourage to remember something you can derive, but if you derive it in the examination, you will be losing so much time. So you just, if you have pen, paper, something, write this equation down and try to remember. Okay? Yes. Very good. That's the equation. So I will just write down. So if any of you has some pen and paper, you can also write it down. Minus zeta omega nt. I will write both the expressions, like what Ragib said, and the other expression also. Omega dt minus e to the power, I'm sorry, zeta divided by 1 minus zeta square e to the power minus zeta omega dt, and converting this, I will get what Ragib said, zeta omega nt divided by zeta square sine omega dt plus theta. So, where omega d is equal to omega n root over 1 minus zeta. So, this expression you need to remember by heart, because if you remember this, then your gate examination questions will be in few seconds, and in the examination, in your examination, like classroom examination, you will solve the problem easily, and you can verify. So, uh, the rise time, you can put yt is equal to 1. Here yt is equal to 1. That's why when you put yt is equal to 1, uh, and then you get the time, corresponding time, that expression you will get is pi minus beta whole divided by omega d, where beta is nothing but the, okay, I'll write the other expression, the original one, omega d tan inverse 1 minus zeta square divided by zeta. So can somebody just calculate it? We have calculated zeta as what the value? 1 by 2, and omega n is equal to 3. So can somebody just calculate it and confirm, so that I will know you guys are following? Yeah, you can verify. The rise time will come 0.8 seconds. And do not forget the unit. I have seen many times students write TR is equal to 0.8. That's it. No, you may lose marks in your classroom examination, because without a unit, the value doesn't have any significance. So you, if the teacher cuts, like gives you 0 mark also, then also he is right. Okay, you can't argue. Yes, 0.8 seconds. Okay, so yeah. So we can approximate it to 0.8 seconds. So keep in mind, do not forget the seconds, units. Okay. Then what is the second question? The second question was the sorry, the peak time, peak overshoot, and settling time. So the question D is peak time. Uh, so the peak time is this. The first, the time at which the system response goes to the peak value, that is called the peak time TP. Okay. Does anybody remember the formula? Otherwise, you can do what you can do is for the maxima or minima. Uh, yeah, by minute. Very good. So what I can call, like, you know this expression, you can make the derivative zero and get the maxima. Okay, global maxima. So it's as he said, it's pi minus beta by omega d. Uh, Sorry, the pi by my bad, pi by omega d is equal to, and can somebody calculate it? Pi by omega n root over 1 minus zeta square. Okay. Uh, you can verify it. It's coming 1.2 seconds. Okay. Again, don't forget the units. I'll give you a small trick. If you want, if you can calculate, whatever the question is given, plot the poles and zeros. Okay. खास करके poles, like the system, and get the poles. Okay. uh, as I have described in the initial part of the class. Then this is omega m, this is omega d, and this is zeta omega n. Okay, this is beta. Then this formula is pi minus beta by omega d. So if you have the plot, if you have this plot, you have the poles, then you can directly calculate that. Here also you can calculate pi by omega d. Whatever this value is, you direct put it and you will get. Okay. Then coming to the E part, and maximum overshoot. What's the maximum overshoot? The formula is e to the power minus zeta pi root over 1 minus zeta square. So you can verify it's coming one, because I have done the calculations. It's coming 160. And most of the time the questions are being asked in percentage. So it's 16.3%. Okay. Then it's asked the settling time. Settling time, whenever the question is asked for the settling time, in general, they have specified whether it's a 2% margin or 5% tolerance, like 2% tolerance or 5% tolerance. For 2% tolerance, what's the formula? And 5% tolerance? Very good, very good. 4 by zeta omega. Okay, for tau is 1 by zeta omega. And for 5%, it's 3 by zeta omega. So can I get the answers from anyone? The zeta is half and the omega n is 3. Okay. Vidya is saying it's 2.7. I would make it 2.67 because that's more accurate. Yes, 2 seconds. Okay. So this question is done. This kind of questions you can expect from in your regular college examination as well as in GATE examination, and this is one of the favorite questions. Okay, now coming to the second question. Okay, I have missed the expression. One second. Okay, so okay, the question says, consider this system. comment on its stability. So whenever the stability of the system is asked, the first thing you want is its pole location, and if the poles are on the left hand side, it's stable. On the right hand side, it's unstable. So the responses also I have shown you in the starting of the class. So let's do the Laplace transformation. It's s square y of s, and I have assumed the zero initial conditions. S y of s plus 1 y of s is equal to u of s. That means the system transfer function g of s is equal to y of, yes, very good. It will be stable. And how did you know? Very good. Root 3 j by 2, not 3 by. Okay. Okay. Cool. So you can calculate, and as you can see, it's the poles, like it's the pole locations. If I plot the poles, then it will be around like this. That's why. And remember, I mentioned whenever poles are complex, they exist in complex pairs. So this kind of pole locations, and as it's in the left hand side, it's stable. Now I will give you some trick. Okay, how to know, like this is a necessary, like whenever the denominator, okay, the denominator has positive, all the coefficients are positive of s square, s, and s to the power 0, then it's stable 100%. It's a trick applicable for the second order system. uh, don't apply it for the third order or fourth order system. You need to verify that. But for the second order system, it's a trick. If it's all the coefficients are positive, it's stable. I'm not saying if all the coefficients are not positive, it will be unstable. No, then you need to verify. But when the question comes like this, but and it has all the coefficients positive, 100% is stable, 100%. It's never goes wrong. So I will write down. So if you can write also, it's a trick. If all the coefficients of denominator is positive, are positive, my bad, are positive, system is stable. It's a trick. That's why writing down the equation, I knew it's a stable system. So just one tricky question. What will, like, if the system is minus s square minus s minus 1? Okay, this is the system. Can anybody say it's stable or not? Anyone else? Vidyadhar or Balkiran, Ragiv, Agam? Hmm. Okay, okay. Hmm. Okay, okay, okay. No, but the trick is like, okay, Balkiran says it's unstable. Okay, and Vidyadhar says it's stable. Uh, Actually, it's the same equation, because what you always do is you equate your denominator to 0. So it's the same thing. S square plus s plus 1 is equal to 0, or minus s square minus s minus 1 is equal to 0. Okay, I just so take minus 1 common. S square plus s plus 1 is equal to 0. That's why it's same equation, s square plus s plus 1 is equal to 0. 0 by minus 1 is equal to 0. It's the same system. I just multiplied a minus 1 everywhere. But if I make it plus, then you need to calculate. Then you can't just comment just by C. Okay? When all the coefficients have same sign, positive or negative, then only this trick is applicable. Okay? Because sometimes gate kind of gives such kind of questions. Just by looking at it you can answer. It will take maximum 30 seconds. You'll save time. Okay. Okay, coming back to the question. Mm, is it clear? Can I get some yes or no's? Okay, Ragit says, and okay, Vidya also says yes. Okay, thank you. Okay, next, coming, this question is done. This is stable. Okay, next come to the second question. The second question says, a unity negative feedback closed loop control system is designed with the above system using a proportional control. So before going to the question, I'll explain like little bit, give hints some about controller. Uh, I don't know whether you have attended the last online session or not. There, I had explained a little bit of. Okay. Yes, yes. Like I have taken similar questions only. Whatever are there in your assignment, fourth week assignment, I am taking the similar questions so that you it will be easy for you. Like you can see, like from week one, week two, week three, week four, all the questions are somewhat related. I am not giving the direct questions from the assignment. I am tweaking a little bit so that it will be helpful for you. Okay. So this is plus, this is minus, and this is, so this is called controller. There are different kind of controller. Sir has taught all the PD, PI, PID. So all of them have different properties and all. You will get to know more about it as the course progresses. So what it says, the question says, my controller is proportional only. That's why I can write my C of S is equal to Kp only. I don't have anything else. I don't have the derivative term nor the integral term. No S, no 1 by S. Okay, simple. Kp. Then what the question says, find the range of Kp for which the closed loop system would be stable. Okay, let's see how many of you remember. If what is the closed loop system U of S and this is Y of S. What is the closed loop transfer function? Hmm? Can you repeat? C of S plus G of S, then C of S. Yes. Hmm. Oh, yes. Yes, it's one. Yes. Yes. Everybody knows in the last lecture, actually, I have explained, last online session, I have explained this part. So you can go through that. So, so now if I do the calculations, so what will be my closed loop transfer function? C of S is Kp, and my G of S, I know it's 1 by S square plus S plus 1 whole divided by 1 plus Kp whole divided by S square plus S plus 1. So it will be Kp divided by 1 plus, sorry, S square plus S plus 1 plus Kp. Is it correct? I guess I'm correct. So my closed loop transfer function is equal to Kp divided by S square plus S plus 1 plus Kp. Okay. Now what we want for what values of Kp the system will be stable. Okay. So for the system need to be stable, what is our condition? I have repeated again and again. All the poles needs to be on the left hand side. Okay. So let's calculate where are the poles. If you have pen and paper, just calculate along with me. How can you conclude that 1 plus Kp must be greater than 0? Hmm. Yes. Yes. Okay. Cool. What Raghib says is this value, because this corresponds to the omega n of the system, the natural frequency, omega n square. So as the omega n square can never be negative, that's why 1 plus Kp needs to be positive. But this doesn't guarantee, does this guarantee stability? Does this this is the condition omega n square will not be negative. But does this guarantee stability? Uh, you can okay. So let's forget about zeta now. Just remember, 5 minutes back I have given you a trick for if all the coefficients, all the, yes, stable, 100% stable. So what I can write, the this coefficient is already positive, this coefficient is already positive, so if this coefficient is positive, then I can say it's 100% stable. So for that I will get again the same expression 1 plus Kp that needs to be greater than 0. That means Kp needs to be greater than minus 1. Okay. But how would I this is a trick I have. So whenever someone gives you some trick, you need to verify, because I just told you, but I what I want is I want to prove you the if you get through the actual procedure, you will end up end on the same answer. So what I will do, let's calculate the pole. If my poles are on the left hand side, then it's stable. So I'll just verify S1, S2, the both the poles minus 1 plus or minus 1 minus 4 into 1 plus Kp. This whole divided by 2. So this is minus 1 by 2 plus or minus root over uh, minus 3 minus Kp, 4 Kp. This divided by 2. Okay. So just check if okay, now the different conditions. If this is imaginary, okay, if this is imaginary, some imaginary, I'll just write this. Let's assume this is imaginary. If this is imaginary, if this is imaginary, if imaginary, then then it's then the system is stable because the real part is minus plus like minus half plus or minus some imaginary, so it's in the left hand side, it's so what happens when it's real, when this value, if this is real, then this whole value must not be greater than half. If that is greater than half, then what will happen? Minus half plus or minus some value a which is greater than half. So minus half plus a and minus half minus a. This value will be positive, which will make my pole on the right hand side. So the system will be unstable. So that's why what I want, sorry, what I want is I want minus the root over of 3 minus 4 minus 3 minus 4 kp whole divided by 2 should be less than half the magnitude. Then I can do 2 is cancelled. I will take the square minus 3 minus 4 kp is less than 1. That means minus 4 kp is less than 4. That means kp is greater than 4 by 4, sorry, minus 4 by 4, which is, that means kp is greater than minus 1. I got the same answer. Am I correct? I got the same answer. So the condition, find the range is kp should be greater than minus 1. Is it clear to everybody? Ragiv, thank you. Ragiv, it's clear to you. But what about everybody? Okay, Vidyadhar, it's clear. So this question is done. Now, what is the steady state error in tracking unit step input for a closed loop system? So the diagram I will just copy because we will draw another diagram. Okay, this is called the error. At this value, this is called the error because it subtracts like my reference u of, this is actually reference, uh, sorry, the reference minus the actual. So that is called the error. So I can write, just I'll keep it as u, e of s is equal to u of s minus y of s. Simple. u of s minus y of s. This is negative feedback, that's why minus. That implies u of s minus c, the actual system that I had. It's okay. I'll just, because it's already time, so I'll just write the e of s as e of s is equal to u of s whole into 1 by 1 plus g of s into c of s. You can verify this expression, simple manipulation here, and you can get the answer. So this is the expression for error, and whoever is from the first class, I have specified a term, like I have mentioned it multiple times. Whenever the term you find steady state, that means you can apply the final value theorem. If you apply the final value theorem, then the solution becomes very easy. And I hope everybody remembers the final value theorem. Yes, yes. So the final value theorem says E of t as t tends to infinite, that is the steady state, is equal to limit s tends to 0 s e of s. Okay. So what I will write s into, what is my u? In the question it's given unit step input. Okay. So the unit step input, so u of s is 1 by s into my 1 by 1 plus what is my 1 plus Kp divided by S square plus S plus 1. So can I get the answer? If I put S is equal to 0, I'll get 1 by 1 plus Kp. This is the steady state error. Is it clear to everybody? Okay. Uh, so this is all what I wanted to discuss in this lecture. So those of you who have joined late, so I will suggest you to go through the lecture on YouTube so that you can get the visualization of whatever I have done in this part, in this section. Like I have taken multiple cases where the second order system's poles can be. It can be purely imaginary or it can have real and imaginary part as well. It can both the poles can be on the same real and it's like okay. I will just write some interesting terms. This is called undamped because there is no damping system. Okay, what this can be called if somebody knows this is called underdamped. Here zeta is equal to 0. Here zeta is between 0 to 1. This is called critically damped. Here zeta is equal to 1. This is called overdamped because there is no chance of getting the like the frequencies anymore. This is called overdamped where zeta is greater than 1. That's why the poles are apart on the real axis. Okay. And I have considered two more cases. One is on the right hand side pole and some both of them are on poles on the right hand side. I have explained the like some responses. I have plotted the system and you can get the visualization. So yeah, if you don't have any more doubt, so I think we can end the session. Okay. Vidyadhar asks, Sir, how can I apply these concepts in real-time system? Can you suggest any research paper or MATLAB example? Okay, the thing is that in here, whatever we are reading is uh, what you can say is LTI system, linear time invariant system. In real life, you will get some non-linear systems. If it is that is linearizable, then these concepts are very much useful. Some paper, research paper, I need to check. Just type in ResearchGate or on Google applications of or significance of real life systems, control system, LTI systems, right? LTI systems, because that's the keyword. Then you will get some ResearchGate links or some Google Scholar link. Then you can check. And MATLAB source, actually, I don't know if everybody is comfortable with MATLAB or they have some exposure to MATLAB. If they are not, then I'm okay to teach them a little bit and give some insights in MATLAB so that they can plot these things in MATLAB. Because if you plot these things in MATLAB, then you will get more visualization and more interested. You will be more interested in the topic. So let's see if some lecture I will try to finish the problems faster and maybe I will explain the MATLAB in that. Okay, Raghav says he doesn't have any uh, prior experience to MATLAB. Do not worry. Just make sure you install the MATLAB from somewhere. If you are a student, your institute has some MATLAB license. You can use MATLAB online in Google. Just write MATLAB online. Then using your institute ID, you can log in. There you can use MATLAB or get somehow in MATLAB installed in your system so that it will be very useful. Like I can, if someday I will explain. Otherwise, you can any day contact me. regarding these doubts. Uh, Sorry, my mail ID, I have typed it wrong. Just a second. The second one, not the first one. Okay, IITK, IIT Kanpur. So you can contact me there. I can share some useful links maybe. Okay, there you can find some topics interesting. I hope you are getting something out of the online session, which is not part of the regular sessions, lectures, and some books. Okay, so if there is nothing else, have a good week ahead and good night. Thank you.